Hello everybody, how are we doing? So it's a pleasure to be here, and I was so happy I could see the announcement even with my photo. I was just wondering, why do they put it so low? So what I want to do is tell you a little bit about some mathematics that I'm interested in. And before we start, I want to just ask the question, why are we doing this? So let's say, why would we discuss geometry 2,000 years after the Greeks? Hasn't everything been studied already? Well, I don't hear any comments. Obviously, the answer is no. We always find new things that we want to study. And in particular, my interest is I want to study these things with computers and do computations and find new things. And so we need to a little bit broaden our horizon and look at the objects that we see and that we know all for maybe thousands of years they've been known, and look at the defining properties. And what the mathematician always do, what the mathematician like to do is take an object that's been well known, characterize it using properties. That means they write down axioms. And then I call this the reverse engineering. If you now forget about that object, you start just from the axioms that you wrote down. If you would now try to classify everything that matches these axioms. Certainly the object that you started with fits. In some cases, you might find new objects that you haven't known before. And that's often the case. In particular, it's the case when we do geometry over a finite field. Professor Maruta gave you some kind of homework, I heard. I hope you all followed up on this advice and looked up briefly what the definition of a finite field is and a group. I heard these words mentioned last time. So when you discuss geometry over a finite field, many things that you take for granted are gone. So for instance, we can no longer talk about the angle between two vectors. In Euclidean space, we have the angle. The angle is defined using the bilinear form. When we are over a finite field, we don't have sine, cosine, and all these things. But we can still distinguish 0 from 1 or 0 from non-zero. So we can still distinguish perpendicular. And so a whole lot of geometry carries through over the finite fields. And what I want to do is give you a little overview of the kinds of things that we study. So I'll start telling you about projective geometry. So we start with the field model. Then we, in particular, we are interested in projective planes. Projective planes then over a finite field of order Q. And we want to look at objects that live in this space. And the objects that we want to look at in particular are the conics. And we want to see if we can possibly find something interesting. Okay, does that make sense? Yeah? Okay, so finite field, let me just give you a little introduction. Finite geometry. So we know the finite fields. They come in two flavors. P prime or Q prime power. And we have a construction of finite fields for every prime power. It was a French guy, and the name was Galois, Évariste Galois. He died very young, I think age 23. And he had the main ideas for finite fields. Then the uniqueness of the finite field of a given order was not proved until the late 19th century by an American mathematician called Moore. Maybe I'll put his name up because he's often forgotten. Moore has proved the uniqueness up to isomorphism of a finite field of given order. So just the easiest case is when P is a prime, the finite field can be thought of as the numbers, integers from 0 up to P minus 1, addition and multiplication modulo P. So what that means is whenever you do an arithmetic operation, what you get afterwards, you reduce this modulo P. Does that make sense? So shall we do a little example? Let's say 3 times 4, we would say we would compute as 12. And if we would now compute mod 5, we would write down congruent to 2. So the answer would be 2. Okay, does that make sense? I think you've heard that. So now what we want to do is we want to talk about an incidence structure. What is this? Incidence structure is a set of points, a set of lines. We can talk about a point being on the line, a line passing through a point. Okay? So I'll have to tell you a few things. Points, set of points, L, set of lines, and I, an incidence relation. We can think of this as a subset of the Cartesian product. The incidence relation tells you whether or not the point is on the line. Does that make sense? Kind of. So if you know the incidence relation, then you can identify a given line with the set of points on it. So you can really think of the set of lines as a subset of the set of points. Every line is a subset of the set of points. So we identify a line with a set of points that are incident with the line. And from now on, for me, a line will just be a subset of the set of points. And then the notation is the following, or maybe language. I would write something like P is on the line. Yeah. From now on, the line is a set. And I would call this, so this is just saying that P is incident with the line. I would say P lies on L, or I would say L passes through P, and all kinds of things. This guy here, P in brackets, is the set of lines that pass through P. So picture here, let's say if this is the point, then this would be the set of lines through the point, and we often call this the pencil of lines. Don't ask me why we call it this way. So when you see P in brackets, this means the set of lines through P. And conversely, if you have a set of lines, let's say T, a set of lines, I want to define the, in square brackets, the union of the set of points in T. And so now, what is my main example? Does that make sense? What is the main example that we want to study is the projective space. Let me just ask you a quick question. Have you heard the projective space before? Okay, yeah, well, it's the same, I guess.
Yeah.
Isomorphic, maybe. So we start from a vector space, and now I want to start right away from the finite field FQ and make it finite dimensional. So a vector space over FQ, and P of V is the incident structure P, L, I. Now I have to tell you what P and L and I is. P is not the set of points in the vector space. P is the set of one-dimensional subspaces in the vector space. So roughly speaking, what happens, you take that vector space, throw away the zero vector, and then whenever you have a vector, you take the direction determined by that vector. That's a one-dimensional subspace, and that's the set of points. Okay? Can I just write down one-dimensional subspaces? Make sense? So what about the lines? Well, the lines are the two-dimensional subspaces. Okay? So and now I have to tell you what the incidence is. The incidence is just the inclusion. Okay? If you want to know what the points are on a line, you have to figure out what are the one-dimensional subspaces that lie on that line. Okay, and in this world, this would tell you what the set L be. Okay? So what we observe here is that if I take x in V, let's say non-zero, then the span of x is the same as the span of lambda x for every non-zero scalar. In other words, we have a little bit of an issue. The one-dimensional subspace, if I want to talk about a one-dimensional subspace, I don't have a unique representative. So give you an example. I could say, let's say 1, 2, 3. If I want to talk about 1, 2, 3, then mod 5, it could also be something like 4, 3, 2. Why is that? Well, just try to multiply them by 4. You get 4. 4 times 2 is 8. Mod 5 is 3. 4 times 3 is 12. Mod 5 is 2. So I would consider these the same point. And people would then call these the homogeneous coordinates. So sometimes you will see that people write something like 1 colon 2 colon 3. In particular, algebraic geometers would like to do that. The thing to notice about homogeneous coordinates, they are not well defined. They are not coordinates. The ratio between any two is well defined. Because when you form the ratio, then the multiplication by lambda cancels out. Okay, but nevertheless, we'll have to work with these guys. And now, so these are called homogeneous coordinates.